we saw on the videos, a laser is used to make a mark on semiconductors, and then a reader verifies these marks. And to verify these marks, as we saw in the video, a measure called unused error correction is used, and as in this problem states, it goes from 0 to 1. Now, according to problem 6.22, an experiment of 2 to the 4 factorial was run to actually observe how this response variable, the USC, responds to changes in laser power, pulse frequency, cell size, and writing speed. So this data, it's not in order, it's the standard order, it's 1, 2, 3, 4. So we need to order that and then copy that to an Excel. So here it is, the Excel. Now this problem is an unreplicated problem, so we need to make a Daniel's test first to see which factors appear to be important. So we're gonna add as many columns as factors we have. In this case we have 4 factors, so we add 4 columns. Now we start with the first column, which this process is called the Yates algorithm. So the first process is to add by pairs. So we have added the pairs. Now we subtract by pairs, but in this case it's the lowest, the one in the bottom, minus the one in the top by pairs. Now we select the whole column and we drag to the right. Now this number is called the grand total, which is the sum of every data. So we're gonna color it with a different color to identify it. So if we did the sum of all this data, it has to be equal to 11.46. So that's the grand total. Now we have to estimate the effects. The formula for the effects is contrast, which are these numbers. These numbers are called the contrasts, divided by n, which is the number of replicates, times 1/2 to the k, where k is the number of factors. So n equals to 1 because we have only one replicate, it is an unreplicated design, and k it's equal to 4 because we have 4 factors. So the effects equals the contrast over the number of replicates, which is 1, times 0.5 times 2 to the 4, because 4 is the number of replicates. The number of factors, not replicates, the number of factors. So 1 time, okay. And this, we copy this column in here. So the effects of A, the effect of A is 0.16, the effect of B is 0.02, and so on. Now from looking at this, just by looking, we can see which effects are significant by their magnitude. So for example, the typical effect ranges from 0.02 to minus 0.01, but for example we have 0.16 and we have 0.13. So these effects of A and C appear to be, from just seeing, appear to be big, but we have to do that. We have to perform Daniel's test to actually observe which one is significant. So to perform Daniel test, we have to make a chart from 1 to 16, because we have 16 data. Then we copy paste just the values of the effects, paste special, just the values. Oh, in this case it's going to be 15 because we're not considering the first one. And then, so this is a place, this one is the effect, and this one is the probability, which is 1 minus 0.5, oh sorry, well, it's, in this case it's place minus 0.5 divided by 15. So let's see, we're gonna make this a little bit prettier with just 2 decimals, and then we're gonna filter, we're gonna sort this one from least, from small to high, from least to effects. We have to the column of effects from smallest to largest. Okay, so that's it, it's in order. So we're gonna graph this one, scatter graph, and yes, so for example in here I'm gonna edit this graph to make it prettier. So we're gonna edit format axis from minus 0.2 to 0.2, and then on minus 0.2, and from, now remember this, we have to actually plot it in a normal paper, but since Excel doesn't have a normal paper, we have to do it on a scatter. So now what we're going to do is we're going to trace a line, and the line has to go through as many points as possible. It's not from the highest to the least, it's just where the where, for example, in here, as much points as possible through the line, not from the highest to the smallest, just as many points as possible. And from here we can see that these points, these 4 points, do not go follow a straight line. So those points are the variables that have an important effect. So for example, in here, this one, this tiny little dot, it's the a variable, which in this case it's laser power. So we can see that A, since the beginning, we saw it has a significant effect, and then these three, which are C, D, and an interaction with AC. So this one, it's Daniel's test on location, because we're seeing which one are significant. And from here we saw, yes, we saw that A is significant and C, D, A, C are also significant. Okay, so now we have performed a Daniel's test, and we have found that factor C, factor D, and the interaction between factors A and C is significant. So now we have to perform ANOVA. We have to make an ANOVA. We have to make an ANOVA table to test if this was correct. So we have to make an ANOVA, and so the first column, it's the sources of variation, and since it's just factor A, factor C, factor D, and factors and interactions between factors A and C, error, and the total. Now we have to make the sum of squares. The sum of squares, we can calculate it from here. Sum of squares, it's equal the contrast squared divided by n, which was 1, times 2 to the 4, because we have 4 factors. And we drag, so, but we only need the sum of squares of factor A, sum of squares of factor C, sum of squares of factor D, and sum of squares of factor AC. So factor A, it's 1, factor C, it's 0.07, factor D, 0.05, and factor AC. Okay, now we have sum of squares. We have to calculate the sum of squares of the total, which is the sum of squares of all the data minus the grand total squared divided by 16, because we have 16 data. And now we have to calculate the sum of squares of the error, which is this one minus this, and so on. And the degrees of freedom, remember that we had to perform Daniel's test, because in an unreplicated design, we don't have enough degrees of freedom to perform an ANOVA on all the factors. So we perform Daniel's test, and this way we have enough degrees of freedom for the error. So A has 1, C has 1 degrees of freedom, D has 1, AC has 1. Total has 16 minus 1 degrees of freedom, and so this one has, the error has 15 minus 4, which equals 11. Now we have to calculate the individual variance. The individual variance, it's the sum of squares divided by the degrees of freedom. And then we have to calculate the f for each factor, which is its individual variance over the individual variance of the error. And we're gonna mark it. And just by looking, we can see that everyone it's very high, so every factor is significant, but we still can calculate it. We have to calculate the f of degrees of freedom, no, of 0.05 with 1 degrees of freedom in the numerator and 11 on the denominator. And so this equals to f dot inverse 0.05 11, and this equals to 0.004, which indeed every number is higher than 0.004, and because of this we reject the null hypothesis, and the null hypothesis states that they were not significant, but since we reject them, they are significant. Now, with this, we can write a regression and equation, which is called the regression model. And with the regression model, we can calculate the residuals. So we have to calculate we have to write the equation. So y expected, it's going to be equal to the average of the data plus 1/2 of every significant effect. So we have to write this equation 16 times. We have 16 data, so we write it 16 times. That's too much. So these are 16, yes indeed. And we have to calculate the average of the data. The average of the data is equal to the grand total divided by 16. And so in here, it's going to be that number. And we just drag it. And then we have to add the plus sign. It's going to be 1/2 the effect of A. So it's going to, we have to calculate 1/2 the effect of A, which equals the effect over 2. So we select it. We dragged it. And we write the variable xa. And in here, what's going to be, it's going to be the signs of the A factor. So we select the signs and we drag. Then plus sign. So we're going to do this for every significant factor. The next significant factor is C, factor C, 0.5 effect of C. So it's going to be 0.5 times effect of C. We go to the effect, we write it, we select it, and we do this on none. And here it's going to be the signs of the C factor, which are this one. And we just drag and drop plus sign. And then our next significant factor is factor D. So we have to calculate 1/2 half effect of D, and it's 0.5 times effect of D. We select it, we drag, and then our last one, it's going to be the interaction of, oh sorry, I'm missing here the variable xd. So the xd with the signs of D. Now in here I got wrong the signs of D, because it should be minus, 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 1, 1, 1, 1. So 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. And the signs of D. I'm sorry for that. So the signs for D should be the 8 first negative and then the next one's positive. Then we add 4 AC, and the 1/2 the effect of AC, it's minus 0.02. From here we have effect of AC 0.05, so yes, the effect is 1/2. And we dragged, replace AC times the signs of A. So in here it's going to be the signs of A times the signs of C. And that's it. So this is our regression model. With this equation we can then get the expected values, and after that we can get the residuals. So in here this is going to be equals of this plus this times this plus this times this. Oh, hold on. Here it's okay. Plus plus and in here we're missing the okay, and this is our expected values. Now to get the residuals we have to do the observed minus the expected. So for simplicity we can write the observed, the expected, and then the residuals. Okay, now I'm going to erase this because this is for the next point. Okay, so the observed are the original data, then the expected are the ones we just obtained, and so the residuals are observed minus expected, and we obtain our residuals. Okay, now we have to check on the adequacy of the experiment. So for the problem they ask us which factors are significant, which we have already identified as A, C, D, and the interaction between A and C. Now we have to analyze the residuals, and we have to check for the model adequacy. That means the normality test and the dispersion test. So the normality test, we have to plot the residuals on a normality paper, but since Excel doesn't have a normality paper, we do it in here. So we write in here, for example, in this time it's going to be place and 1 through 16 because we have 16 expected values. Then the residual, we're gonna copy here just the values because we have to then sort the residuals from lowest to highest. And here we copy values, very special values, then the probability, which is equals to the place minus 0.5 divided by 16. And then we plot the residual against the probability. Oh wait, hold on, I forgot. Yes, I forgot to sort the residual from smallest to highest. We sort it from smallest to largest, continue with current selection, and then we make the graph. And as we can see from plain sight, we can see that it indeed follows kind of a straight line, but still we have to do it. So this is the normality test. Now remember, we have to do this on a normal paper. Now we have to format the axis from -1 to 0.1. Then we make it cross on -0.1. And the y-axis, we have to make it go to 1. So that's it. Then we have to fit a straight line through as much points as possible, not from highest to lowest, but from the one that passes through most points. Now we can see that most follow the straight line except this point, but if we check its normal contribution, it's still on the, how do you say, on the range. So the normality test is okay, the normal distribution is okay. If this point wasn't under the normal distribution, it may be an error of the experiment, but since it's just this point, it doesn't matter. That the designer should have to revise this point, but the others follow a normality distribution, so it's okay. Now we have to check the dispersion. There's two ways to check the dispersion. The dispersion, we can for dispersion we can apply the dispersion test or just plot the residuals against each factor. So we're going to do it that first, and then we're going to do the dispersion test. To do that, we have to plot the signs of A, and these are the ones we have over here. Against the residuals, and we copy the residuals, and then we plot this on a scatter graph, and we observe the dispersion. In here we can observe that A on its low level, which is 9 watts, has a significantly lower dispersion than A at its highest level. So A does affect dispersion because it has one factor, one level that affects most in here than the other. But we still have to check this with the dispersion test we're going to do later. And we continue this with every factor. Signs of B, then residuals, and then the graph. Residuals, and then the graph. And in here we can also see that B affects dispersion, since B at its high level has a lower dispersion than B at its lowest level. Okay, so that was B. Now let's do it for C. Signs of C. Then residuals. Then graph it. And in here C also appears to affect in dispersion, since C at its low level has a lower dispersion than C at its high level. Now for the last one, for D. See the signs of D, remember that I changed this from the original because I had it as it was of C, but I changed it. Signs of C, 1, 3, 4, 5, 6, 7. Okay, that's correct. Signs of D. Residuals. And then we plot it as scatter graph. And in here we can also see that D may affect on dispersion, but because D at its high level has a lower dispersion than D at its high level. Now remember, we have to check the distances between the highest and lowest points. For example, A has a significantly lower distance in its low level from here to here than its high level from here to here, and the same goes for each one of the others. Now for the dispersion test, we are going to have to copy dispersion test. We're going to copy this, but we're gonna transpose it. So we're gonna copy it, then we're gonna paste special, transpose. And what we're going to do is we're going to write the signs of A under A. The signs of A under A. Then the signs of B under B. Then the signs of AB, it's equal the signs of A times the signs of B. Then the signs of C. The signs of AC, it's the signs of A times the signs of C. BC, it's equals the signs of B times the signs of C. ABC, it's equals the signs of A times the signs of B times the signs of C. So A, it's the signs of A times the signs of B. Then AC, it's the signs of A times the signs of C. And BC, it's the signs of B times the signs of C. And ABC, it's the signs of C, A, B, and C. Okay, so we dragged, then sines of D. Now the sines of A times the sines of D, sines of B times the sines of D, now in here we can do it both ways. We can multiply sines of A times B times D, but it's simpler if we just do the sines of AB times the sines of D. And we continue the sines of C times D. Now the sines of, for example, AC times D. Then BC times D. BC times D. And the sines of A, oh, hold on. The sines of ABC times the sines of D. Now we're gonna put in here the residuals to visualize it better. The residuals here, then here also. And what we're going to do is we're going to calculate the variance when the variable is high. We're going to calculate the variance when the variable is low, and then we're going to calculate the f. Just hold on, I'm going to make sure it's called f. Yes, the f asterisk. We're gonna f asterisk, which indeed the f are going to be the dispersion effects. So we're gonna equals the variance when A is high, so it's going to be on the residuals. So it's going to be 1, skip 1, skip 1, select, skip 1, select, skip 1, select. And oh no, none. Okay. Then we're gonna do it when the variable or the factor is low. So select 1, skip 1, select 1, skip 1 for A. And then the f is going to be the natural logarithm, natural logarithm of this divided by this. And we're gonna do this for all the data. So for example, V, it's going to be the variance when B is high. So it's gonna be skip 2, select 2, skip 2, select 2, skip 2, select 2, skip 2, select 2. And then the variance when it's low, it's gonna be select 2, skip 2, select 2, skip 2. And it's going to be the natural logarithm of this one divided by this one. Okay. And we're gonna do for C. For example, C, it's easy because it's gonna be when C is high, skip 4, select 4. Skip 4, select 4. and when see it's low, it's select 4, skip 4, select 4, skip 4. Then it's going to be natural logarithm of this one divided by this one. Oh. Okay. Now we do it for D because it's also easy. Variance D, it's gonna be select A, skip 8. 1, 2, 3, 4, 5, 6, 7, 8. And then variance when D is low, which are the first 8. 4, 5, 6, 7, 8. And then natural logarithm divided by this one. Now the other ones are a little bit more complicated because you have to see where B is high and where AB is low. For example, in here it's this one, AB is high, then 2 they are low, then 2 are high. So we have to be careful, it's not a clear pattern. Too low, too high. In here, too low, too high. Too low, 1 high. And we do this for when AB is low, which is are too low, too high, too low, too high, too low, too high, too low. And then we do the yes. And we continue with the rest. Once we have all the dispersion effects, we have to perform a Daniels test on the dispersion effects. So we have 15 dispersion effects. We're gonna plot 15 data. Then we have the dispersion effect, which we're gonna plot it. Oh, we have to transpose them. Copy, paste special, values, transpose with this on the side. And the probability, which is equal to 1 minus 0.5 over 15. And these ones we're gonna sort them from lowest to highest. Okay, so we have to actually select from up here, sort, custom sort, the dispersion from smallest to largest. And then we plot on a scatter graph, and we can observe that they indeed follow a straight line. They follow. Oh, okay, so in here I know what I did wrong. I did wrong on the probability, which it should be place minus 0.5 over 15, and then we do this. Yes, that makes more sense. And then we actually graph it, and we can see, well, we have to make this look prettier. I will say here minus 2.5, axis minus 2.5, and then we have to make this for my axis go to 1, and this is Daniels test on dispersion. And we have to fit a straight line through as many points as possible. So we're gonna fit a straight line through as many points as possible. We can see that indeed, as we said in the beginning, this point, which is A, it's out of, how do you say, it does not follow a normal distribution, so A has a significant effect on dispersion. Then we can go and we'll see where, and we can say maybe these points are going to be, they're not exactly on the line. For example, this point has to be 1, 2, 3, 4, 5, 6, 7. So 1, 5, 6, 7. It's A, B, C, D, but controlling dispersion and fourth factor, it's really complicated. Then we can say maybe this factor affects dispersion, which is factor B. Then we can say yes, well, factor B can also affect dispersion, but otherwise it follows a straight line, and the one that we can clearly see, it's A and probably B. So A and B affect dispersion, as we saw in here. A affect dispersion, and B, yes, it on a less amount than A, but it does affect dispersion. So now with this on mind, we can make recommendations, but first we have to obtain the averages. For example, we have to obtain the average for every significant effect and interaction, which was average of A when it's high, average of A when it's low, and for every significant effect, which was C, average of C low, D, average of D high, of D low. And for the interaction, we have to make average when A is high and C is high, average when A is high and C is low, average when A is low and C is high, and average when A is low and C is low. So with this, we obtain averages of A when it's high, which means skip one, select one, skip one, select one, skip one, select one. And average when A is low, which is select one, skip one, select one, skip one. And we do the same for, well, in here we can see that we have similar effects, but since on the problem we assume we want to minimize the UEC, the response value variable, since we want to minimize, we have to then select A minus, because A, when it's in the low level, has a lower average. So we select A minus. So we select, I don't know, this one. Then we do this for the C plus when C is high, which means skip 4, select 4. Skip 4, select 4. Then when C is low, which means select 4, skip 4, select 4. And in here, since we want to minimize, we select C on its high level because it has a lower average in here. Then we do it for D. D, when it's high level, it's skip 8, select 8. And then on its lowest level, it's select the first 8. And in here, since we want to minimize, we have to select D on its high level because it has a lower average. Then we go in here, we have to do the average when both A and C are high. To do that, we can do a little trick, and then we can go and see the standard order, and both A and C have to appear. So for example, in here, A and C appear, so we select AC, and then AC both have to appear in AC, ABC in here. So this one, we select this one, then we select this one, and we select this one. Both have to appear. Now in this one, average when A is high and C is low, we have to select the ones where A appears but C does not appear. So for example, in here, then in here, then A appears, C appears, A in here, then A in here. And then we have to do the average when A appears, A does not appears, and C does appear. So for example, in here, C appears but not A. In here, C appears but not A. In here, C appears but not A. And in here, C appears but not A. And then we select the ones where neither of them appears. So for example, in here, A, neither C appears. In here, neither one. A in here, and in here, PT. Okay, yes. So from this one, if we want to minimize, we'd have to select A minus, C plus, which is A at its low level and C at its high level, which is what we obtain here. And now on dispersion, we have to consider also dispersion. In here we obtain that A and B has an effect on dispersion. B, we would have to select, since it doesn't appear in here, we go to the graphs of dispersion and we'd say, well, B plus has a lowest dispersion, so we select B at its high level. We would have to select B at its high level, and then we would have to check the dispersion for A, and in here we clearly have that A at its low level has the lowest dispersion, which is what we have obtained in here. So that's that completes this part. The recommendations would have been as A on its low level, which means 9 watts, C at its high level, which would be 0.12 inches, B at its high level, because B at its high level has the lowest dispersion. B at its high level would be 12,000 hertz. Then D at its high level, which would be 20 inches per second. And well, the last thing that we could do, it's a contour plot. Okay. Now for the contour plot, we're gonna need the model regression equation, which is this one. We're gonna copy it. We're gonna paste it down here. Paste special just values. And what we're going to do is we're gonna write a table from -1 to 1 and from 1 to -1. I'm just gonna check that's right. Yes, from -1 to 1 on the x-axis and from 1 to -1 on the y-axis. Now this depends on how big do we want it to be. Let's make in here a 20 by 20 table. So for example, we're gonna write -1 in here, and we have to divide 1 to -1 in 20 exact places. So for example, it's gonna be 2 in here I'm gonna calculate, so it's gonna be 2 over 20, so 0.1, so it's here it has to be this one plus 0.1, and we're gonna do it until we have 1 in here, which then we select, and indeed they are 21. And in here we're gonna do the same, but from 1, and in this one it's going to be this one minus 0.1, and we're gonna do it all the way until -1, which is until here. Now what we're going to do, it's since AC showed to be a valuable interaction, we're gonna plot the contour plot of A against C. For contour plot, we have to plot it against two variables, and since AC have a significant interaction, we are going to plot in here as an example the contour plot of A against C. So it's going to be, we're going to select the first one, and we're going to select the average, and then we're gonna add the effect of A and multiply it times the number on the top of the column, of that column. So it's going to be that effect of A times, and since we want it to vary from column to column, we add a $sign on the between the variable and the number, and then we're gonna do the same for the C times, but it's going to be the number on the left of that row, and we're gonna select, and then in here it's going to be on the left side, and we click enter, and it has no, okay, and then we scroll it, and then we down until 141, until 141, and we have our contour plot, but now we have to actually paint it, and we have to see some lines, and in here we can see that since here we said the lowest interaction, it has to be A minus. With C plus we go A minus, which is in here, A minus, and C plus, which is in here. A is this one, C is this one, so A minus C plus, it's 0.57, which it's about right, and the highest interaction has to be A plus, but in here it's the one we consider. Now we have to paint it, and we have it goes from here, from highest 0.86 to lowest to 0.57, so from here all the way to this corner, and so we can see it's 0.57 and 0.86. We can say, I don't know, divided by, that's about 0.20 of difference. We want 5 lines, it's going to be 0.04, so I'm gonna say we're gonna color all the 0.6s, which we're gonna do conditional formatting between, so we'd say 0.6, I would say between 0.59 and 0.61, oh, hold on, and 0.61, and then the next one would be between, I would say, so for example, the difference between 0.57 and 0.86, it's about 0.20, and I said I wanted 5 lines, so I divide 0.20 over 5, and that gives 0.04. So I'm gonna choose intervals of difference of 0.04. So for example, I first chose 0.60, now I'm gonna choose 0.64. So to color 0.64, I'm gonna color between 0.63 and 0.65. And I'm gonna do that on and on. So it's gonna be 0.67 and 0.69 and then it's 0.71 and 0.73. Then it's going to be 0.75 and 0.77, and then it's going to be 0.81, 0.82, 0.80, it's going to be, no, hold on, it's 76, so it's going to be 0.79 and 0.81, and then it's going to be the last one between so it's going to be 85, 0.80, 0.84, so it has to be 0.83, 0.85. So yes, indeed, we have a contour plot with straight lines. And now the last part of the problem has to do with the pure quadratic test. So for example, on problem 6.23, we are asked to reconsider the experiment in problem 6.22 and add 4 runs, which are 0.98, 0.95, 0.93, and 0.96. And they ask us to reanalyze the experiment and test for curvature. So what we have to do is we have to make an ANOVA and a new ANOVA and add these points. So for example, it's 0.98, 0.95, 0.93. So we're gonna do it in here. We're gonna copy our, we're gonna do now an ANOVA with all the points. So ANOVA source of variation, we're gonna do every single one. We're gonna do every single one. Yes, paste. Then we're gonna add here the pure quadratics, the pure error, and the total. So in here we have the sum of squares, and in here we already calculated the sum of squares. In here we just click it, the ones we have, and to calculate the sum of squares of the pure quadratic and the pure error, we have to analyze the points which were given here. So it's 0.98, 0.98, 0.95, 0.93, and 0.96. And 0.96. So what we have to do here, we have to obtain 4 new variables. So we're gonna call NF. It's going to be equal to the number of points in the factorial on the original factorial, which are 16. 16 are the original points, and NC, it's going to be equal to the number of points added. So we added 4 points. Now we have to obtain the average of F and the average of C. The average of F equals the average of the original points in the factorial, and the average of C equals the average of the new points, of the added points. So now with that we can obtain the sum of squares of the pure quadratic, which equals to NF times NC times parentheses the average of S minus the average of C close parentheses squared. I'm gonna add here another to make sure, another parenthesis. Then this is going to be divided by NF plus NC. And we obtain our pure quadratic, sum of squares of our pure quadratic, and the pure error, the sum of squares, it's going to be equals to every data of the points added minus its average, which average of C squared. Plus this, oh, I'm gonna do parentheses, minus this squared plus this minus this squared plus this minus this hold on, squared, 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 squared. So each one, and then the total, it's just the sum of all these. And now the degrees of freedom are going to be the same in here all the way until here. Total, it's going to be, now instead of 16 it's going to be 15, it's going to be 20 minus 1, which is 19, and then in here pure quadratic, it's going to have 1 degrees of freedom, and the pure error, it's going to have NC minus 1 degrees of freedom, so it's going to be NC minus 1 with 3. Now we calculate the individual variance, which is going to be this one over this one. Then we calculate the F, which is going to be this one over this one. Hold on. I wrote something wrong, I think. This one over this one, and this one has to be, okay, I know what. So it's this. And then the F, we calculate the F for 0.05 with 1 degrees of freedom, with, and then the error now has 3 degrees of freedom. And so this one is going to be F inverse 0.05, 1, and 3. So apparently, so we compare if this one, if we write it, if this one it's larger here larger than this one, we reject, we reject H0. If not, we do not reject H0. And we obtain that, okay, I think I did something wrong. I know what mistake I did. It was that I select the wrong function, which has to be indeed another one. It has to be f inverse of 0.05, 1, and 3. And then we compare it against, so we have to, I have to actually, okay, so we compare, I'm going to erase this one, and okay, so in the previous ANOVA, in here I also have to correct it, f inverse, this one, 0.05, 1, and 11, and but indeed everyone gave higher than this one, and in here, so with the correct f we check if this value is higher than this value, we select, then, oh, hold on, I guess in here, then we reject H0. If not, we do not reject H0. And we dragged it. And so we can see that since we rejected PQ, it means that there is actually a curvature in the design. So this means that the previous design has to be redesigned into a new one that considers this curvature. We have to add a quadratic term on the regression model. And the last thing I want to comment is that we obtained the same answers as previously, reject A, reject C, AC, and D. And something interesting happened with CD, which now appears that we have to reject it with the new data. So with the new data, C and D also have an interaction, and that also has to be considered in the new regression model. And with this, we're done.